All right, let's dive right in. We're going to talk about something that's at the absolute heart of your computer. It's memory. Specifically, we're talking about DRAM.
You know that feeling, right? You're just staring at a loading bar, waiting for your game or an app to finally kick in. Ever wondered what's really going on behind the scenes? Well, in those few seconds, something incredible is happening. A super fast handoff of information that makes everything possible.
So, to really get it, we're going to go on a little journey. We'll start high level, then we'll zoom right into the memory chip itself, and then we're going to go all the way down to the microscopic level to see how a single bit of data, a 1 or a 0, is actually stored. It's going to be cool.
Okay, first things first. We've got to get one crucial thing straight. Your computer has two main kinds of memory, and they do totally different jobs.
Think of your SSD, your solid-state drive, as like your computer's library. It's for long-term storage. But then you've got DRAM, and that's the working memory. So why do you need both? Well, the computer's brain, the CPU, is way too fast to deal directly with the library. It needs a super fast workspace. So before anything can happen, data has to be copied from that slower SSD into the blazing fast DRAM. That is what's happening when you see that loading bar.
Let's really break this down. Purpose-wise, yeah, SSD is the library, DRAM is the high-speed workbench. When it comes to capacity, SSDs are huge. We're talking terabytes. DRAM, still big, but more in the gigabyte range. Now this is a big one, data retention. SSDs are permanent. You turn off the power, your files are still there. DRAM, on the other hand, is temporary. It's what we call volatile. Power goes off and poof, the workbench is wiped clean. And the real secret sauce behind the speed, it's all about structure. An SSD is a dense 3D stack, which is awesome for cramming in tons of data. But DRAM is a flat 2D grid. That structure lets it access any single piece of data almost instantly. That's the key right there.
And this chart, wow, it really shows you just how big that speed difference is. Getting data from an SSD takes around 50 microseconds. And you might think, hey, that's pretty fast, but hold on. DRAM does it in just 17 nanoseconds. We're talking about two totally different universes of speed here. The gap is so huge you can barely even put them on the same chart.
Let me just put a number on it for you. DRAM is roughly 3,000 times faster than an SSD. This isn't just a little bit better, it's a completely different league.
So how do you even wrap your head around a 3000x difference? Well, think of it this way. It's like comparing a supersonic jet to a tortoise. Yeah, seriously. One is basically instant, and the other, well, it gets there eventually. And that massive speed gap is the entire reason your computer needs both.
All right, so we've established that DRAM is crazy fast, but how does it actually work? Let's zoom in and take a look inside the chip itself.
The best way to think about a DRAM chip is like a massive, perfectly organized city. It's packed with billions of tiny little houses, and every single one has its own unique address. This way, the CPU knows exactly where to go to find any piece of information it needs, instantly.
And this city has a very clear layout. The whole chip is split into these big neighborhoods we call bank groups. Inside those, you've got smaller districts called banks. And then within each bank, you've got this huge, perfect grid of streets, the rows and columns. And that's where all the data actually lives.
So how does the CPU find anything? It uses a 31-bit address, which is basically just like a set of GPS coordinates. Part of the address says, go to this neighborhood and this district. Another part says, go to this specific street. And the last part says, go to this exact house number. It's an unbelievably efficient system for pinpointing one bit out of billions in just nanoseconds.
Okay, get ready. We're going to zoom in one last time. We're going all the way down to the most basic, fundamental building block of memory, the tiny little cell that holds just one single bit of information. And here it is, the 1T1C memory cell. That just stands for one transistor, one capacitor. It's pretty simple, really. The capacitor is like a teeny tiny little bucket that can hold an electrical charge. And the transistor? That's just a gate or a switch that opens and closes to let stuff in or out of the bucket.
And how this works is actually beautiful in its simplicity. If that tiny bucket, the capacitor, is full of charge, the computer reads that as a 1. If the bucket is empty, with no charge, it reads it as a 0. That's literally it. Every single thing happening in your computer's working memory comes down to billions of these little buckets being either full or empty. Now, to manage all of this, the memory controller is working non-stop, doing 3 main things. First, it's reading, checking to see if a bucket is full or empty, a 1 or a 0. Second, it's writing, which just means it's either filling a bucket with charge or emptying it out. And third, and this is super important, it's constantly refreshing the data.
So let's talk about that refresh for a sec. It turns out those tiny little buckets are leaky. They can't hold their charge for very long at all. So to stop all your data from just disappearing, every single one of those billions of cells has to be checked and topped up if needed about every 64 milliseconds. It's this constant, frantic race against time happening inside your computer just to keep everything from being forgotten.
All right, let's pull back out. We've seen the tiny, leaky buckets and the giant city-like grid. So how does all of that microscopic action translate into the smooth, seamless experience we have on our screens?
Think about playing a modern video game. As you're running around, your DRAM is juggling everything you see on screen. We're talking the 3D models of every character, the detailed textures on the walls and ground, the entire layout of the world, where every single object is at that exact moment, plus all the complex lighting and shadows. It's all in there.
And here's the kicker. All that data? It needs to be grabbed and updated millions of times a second. Without the insane speed of DRAM, that whole immersive world would just stop. It would grind to a halt. Your game and pretty much everything else you do would suddenly be 3,000 times slower. The supersonic jet turns right back into a tortoise.
So at the end of the day, it's this mind-boggling speed that makes our modern digital lives possible. And that kind of leaves you wondering, right? As our virtual worlds and our games get more and more realistic and complex, what's the next big leap in speed going to be? And what kind of incredible new things will that make possible?